Okay, yeah, we're going to start a new unit. I think this is the most fun and interesting part of the course that we're getting into now. Especially today's lecture, I think is really cool to put a bunch of pieces together that we've been working on. So in this unit, we have this synthetic data set. This one here. This is a classification data set, so we have some green labels, which I think they're 1, and the blue labels are 0. And the features are just two-dimensional. And the question is, how can we classify this data? So we first learned about logistic regression and support vector classifier, and we know that those linear methods, they just can't do a good job of separating green from blue for this data set because it's just very far from linearly separable. And then we talked about the support vector machine. We said, okay, that's a pretty useful method based on some kernels. Some kernels tend to work better than others. But here, sort of a related idea is, could we somehow do some sort of transformation on this data in order to get it to a form where we could linearly classify it? And so, yeah, we should be able to do that. But the question is, like, how do you get that transformation? So what we're doing now that we've never before done is we're actually going to learn that transformation from the data itself. So that's what's really different. Whereas the SVM, we just kind of plug in this kernel that has some implicit transformation that we just need to trust, or maybe we try several of them. But none of them are really going to be especially designed for the data set we're working with. So what's really cool about this is we're actually trying to come up with a feature transformation that we will essentially learn, and then once we have it, we can then just follow it up with one of our familiar methods like logistic regression, and we'll see that it works really well. So in this case, we're gonna use a very specific architecture for coming up with those that feature transformation. And even for that, we're going to borrow some of the ideas that we have developed before in linear classification. So what we're going to do is we're going to learn 4 transformed features. So we're going to go from 2-dimensional space up to 4-dimensional space. Each of those new features is going to be the soft output of a linear classifier. Okay, so that means that one way we know that linear classifiers, we can visualize them as decision regions. So imagine that I'm just talking about this red linear classifier here. So when we talk about the hard outputs, that would be like y hat, which would be for one side of this boundary, we would get y hat as 1, and the other side of the boundary would get y hat not equal to 1, right? But we're going to use soft outputs. So by a soft output, we mean we're going to put it through our logistic sigmoid, and the sigmoid is going to give us a value that's going to be between 0 and 1. And so when we have this boundary here, that means when we're really close to the boundary, that soft output is going to be close to 5. But as we go farther in one direction, it's going to get close to 1. And as we go farther in the other direction, it's going to go close to 0. Okay, so when you see this, just imagine that for particular x's here, you can visualize that the transformed feature you're going to get is going to be that soft output. And in fact, here are the pictures. These are heat maps of those transformed outputs. So here you can see that that's that red classifier, which is oriented like that. And these colors show you the value of the soft output. So actually, as you go southeast, that is where the soft output is getting close to 1. And as you go northwest, that is where the soft output is getting close to 0. Okay, so this is going to be for one of our transformed features. We're actually going to make 4 of these features. each one of them is associated with a different linear classifier, a different boundary. And so, you can see now these are the 4 features. So that's the first stage. This is a 2-stage approach. So now the first stage creates these 4 new transform features. And then the second stage is just logistic regression. We know how to do logistic regression. Now we have a 4-input vector, 4 features. And logistic regression gives us a final soft output. And that final soft output, if we plot it, it's heat map again. 1 is dark red, and white is 0, and you can see that it is doing quite a good job classifying. So all the samples in this region would be correctly classified as green, and all the samples out here correctly classified as blue. Okay, so that's what we're doing at a high level. Okay, are there any questions? There's a lot going on here, so yes.
Is 4 transformed features like a common thing, or is that just for this data set, like choosing 4 of them?
Oh, that's a great question. It's definitely not a common thing. It definitely is for this data set, but let's think about that a little bit more. Maybe let's pause for a second and answer that question in just a moment when we think about what is happening in the second stage. So from one perspective, in that second stage, it's trying to take the 4 numbers, and these numbers coming out of the first stage are somewhere between 0 and 1, but let's just pretend for the moment that they're exactly 0 and 1. So that would mean that on this side, you would get 0s of the red. On this side, you get 1s. And then for the green, on this side, you would get 1s. Sorry, on this side, you get 0s. On this side, you get 1s. So what is special about this particular shape here? What's special about that?
You get 1 from all 4 features?
Yeah, well, actually, yeah. In particular, let's. It turns out it's not exact. You got the idea. It's not exactly 1 because on this side it looks like we have 0s. Then on this side it looks like we have a 1, and then on this side it looks like we have 0 and 0 again. But it's a particular binary sequence. And that second stage is picking up on that particular binary sequence and saying, like, I'm going to use that to come up with my soft output. So its W vector is going to be pointing in that same direction to maximize the output. And so that is going to give you this nice region here. So you can see that from one perspective, you can think about this idea as an intersection of half spaces. So what I mean is, on the correct side of the red line, that's a half space, in that we've taken this 2-dimensional real space and we've split it into half. But we're intersecting that with this other half space, the one below the green line, and we're intersecting that with the one to the northeast of the orange, and we're intersecting that with the one to the east of the blue. And when you take the intersection of all those 4 half spaces, that's when you get this region. Right, so that's kind of like we're asking the second stage to produce the output, close to 1 for the intersection of half spaces that correspond to our green samples. Okay, so is that making sense? Okay, so now that we have understood that, how many features do I really need in this first stage? How many features does that need to output for this to work well? Does it need 4 exactly, or could I use a different number?
Number of classifiers?
Well, yeah, it is the number of classifiers. So the question is, how many of those do I need? So anybody, I saw people, yeah, so.
Could you use 3 to define a region?
Yes, I could use 3 because you can see with 3, I can still kind of isolate a region here, right? Could I use 2? No, I couldn't really use 2 because, like, for example, maybe if I use these 2, my region looks like this, which is it's like it's going to classify all those blue samples as green, so that's not going to work. So I need 3 is sort of the minimum number for this very particular data set because I need to isolate the points in the middle. And I can surround them with 3 of these boundaries. And that it might not work as well as 4 because the region I'm creating there is a little bit less flexible. It's a triangle. It has less degrees of freedom than this trapezoid. And if I used 5, I could get a shape that has a little bit more precision. And if I use 6, right, as I use more, I can more perfectly craft that shape in the middle. So does that answer your question? Yeah. So you can kind of see how there's definitely going to be a notion of too few features. In terms of a notion of could there be too many of these transform features, what do you think about that? What do we think about when we ask that question? Is there a danger with using too many, and if so, what is it?
Would be overfitting.
Yeah, we could be overfitting because we have a lot. Every time we add one more of these, we have a bunch more parameters to learn. So from the classical bias variance trade-off ideas, we get this conclusion that, yeah, there's probably if I add too many features, too many transform features, I'm going to have too many classifiers to learn. That's too many parameters for the size of my data, and I'm going to be in trouble. There's actually some very recent results, research that says for particular neural networks, for reasons that are not fully understood yet, you can kind of escape this bias variance idea. It's called double descent. So if you think about the typical bias variance that we learned about is like a U-shaped curve. This is something like on the vertical axis, we'd be talking about, we did this for mean squared error, but you could imagine some other loss function. And on the horizontal axis, we'd be talking about number of parameters. And so that U-shaped curve basically says like, if you're too far to the left, bias kills you. If you're too far to the right, variance kills you. You want to be in the middle. But what's interesting is for certain architectures of neural networks, you have this double descent where once you go far enough to the right, actually it starts coming down again. And it actually says what you really want to do is put in like tons and tons of these parameters and rely on some other peculiarities of the architecture and maybe of even the optimizer, that algorithm. They're going to somehow escape that variance issue. So this is like, I'm just mentioning this. It's not something I'm going to ever test you on or ask you about, but it is interesting that the story is a little bit more complex than classic statistics says. And this stuff is really still being actively researched, and it's not fully understood. So, okay, but yeah, so from our perspective, based on what we learned, the answer would be yes, if you use too many of these intermediate features, you could have trouble. But it's actually an interesting thing to try it. I had some grad students try it for simple neural networks a few years ago, and what they found was that you see the classical stuff until you have tons, like thousands, tens of thousands of these intermediate features, and at that point you start to see things change again. So yes, you can see it for some of these neural networks, but you have to sometimes go way extreme sizes. So it is something for your projects you could play with if you wanted. You can see what happens. Okay. All right. Very good. So any other questions on what we have on this page? Okay. Here I'm plotting the weights of the second stage. And you can kind of see when you look at the signs of the weights, it's a little hard to see. This is negative, positive, negative, negative. Those signs align with, it's negative when the middle is more white and positive when the middle is more red. And that's exactly what we expect with the second stage weights aligning with that binary pattern of, what we said, 0, 0, 0, 1, 0. Okay, so that all checks out. Okay, so that's the main idea. So we were basically putting together several ideas that we've seen in the past to break through this linear separability issue that we know linear classifiers suffer from, and also break through the need to know a transformation but actually learn it. So I want to emphasize that, you know, we did not place these boundaries here. These were learned from the data itself. We set up this structure, we plugged in the data, we ran maximum likelihood training, and this is what it learned. It came up with the idea to place these boundaries exactly here. You know, it's not like we told it to do that. We just told it make 4 boundaries and then process those soft outputs within a classifier, and it successfully classified the training data. Okay, so this is all learned. Yes?
So would this eventually give us like the usual x1 squared plus x2 squared equation of a circle that I can kind of see in?
If you, Shane, like if you used many transform features so that you could approximate it like that?
Yeah.
In principle, yeah, it should probably do something that goes in that direction. Yeah, I don't actually know exactly, or I don't remember exactly how the data was generated, but yeah, it should do something reasonable if you give it more features. Yeah.
Would this method of like learning the transform do better than us getting in the transform given that we know something about the data? Using like the kernel method?
That's a good question. I don't know. Like, I'm guessing the kernel method, RBF, would probably work similarly well for this data. So it's just another option. Yeah. Yeah. When you do your project, you know, on a given real data set, you'll be able to compare how the SVM does compared to the neural network, and compare all these methods, and it's going to change with the data set. Some data sets, neural networks can somehow outdo the support vector machines. Other times it's the opposite. They're usually pretty close, but sometimes one has an edge over the other. Okay, great questions. Any other questions? Okay, so so let's just keep looking at this idea now that we understand the idea, and just put some math around it and some notation. So we have special names for the 2 stages. The first stage is typically called the hidden layer. The second stage is called the output layer. If you think about the equations in the first stage, because it's sort of based on the idea of linear classification, the very first part of the first stage is a linear transformation where you take your raw features, you put them through some weight matrix WH, you add some intercept terms BH, and you get some linear scores ZH. And that's exactly what we would do in linear classification to get our scores. So these H's here, the subscript H just refers to the hidden layer. And even the dimension DH refers to how many of these hidden layer or transform features we're creating. So then, again, inspired by linear classification, we're going to put each of those through a sigmoid. We know that the outputs, once I put that linear score through the sigmoid, I will get a quantity that goes between 0 and 1, and we can interpret it as some sort of probability if we like, or just think about it as a soft output, some sort of transformed feature that lives between 0 and 1. And so this is really what we do in that first stage, the hidden layer. There's a linear stage followed by some nonlinear processing, but the nonlinear processing in this case is scalar. So like this scalar value is processed by this sigmoid, and then this next one is processed by this sigmoid, and so on. So the processing is decoupled, you could say. as we'll talk about later, it's actually not essential to use a sigmoid here. You can swap this in for all kinds of other nonlinearities. And actually, a lot of them work pretty well. But this one just helps us connect it back to things we've seen previously. Okay. In the next stage, we take those quantities. These are the transform features. Now we're calling them A. The reason I'm using the variable A is they are called activations. And so we're going to take these activations, and we're going to put them through the second stage of linear classification. And so this is just going to be, since we're doing binary classification, we know that we can just compute a single linear score, and that comes from this equation. All the subscripts O here refer to the output layer. And we know that if we want to, so we could stop there. We could have this linear score here, and we could threshold it at 0. Or we could go one further stage and put it through a sigmoid, and then we have a soft output, and we can think about that as a probability, the probability that the label is 1 given the original input. Okay, so that's 2 stages of processing. They both have kind of similar forms. And in fact, we can think now about this output as just doing logistic classification based on these transformed features, right? This is exactly what logistic regression looks like. And then we can think of this stage as just feature transformation. Okay. People tend to call these multi-layer perceptrons, or you could also call a 2-stage feed-forward neural network. Okay, so just another way to draw the picture. All right, any questions? Okay, so now the question is, well, how do you learn all the parameters? Okay, so what are the parameters? Well, in that first stage, we have this W matrix, then we have a B vector. In the second stage, we have a W vector and a B scalar. And let's put all those together and just call them theta for notational simplicity. So that's what we want to learn is this theta. We have, as usual, training data. So we have a bunch of our raw features and the binary labels yi. And now we can exploit our knowledge of logistic regression to say, well, in logistic regression, we're essentially using this logistic model. Here's our sigmoid, and we know that the linear score is what we put here. What's different about this network is the linear score z is not just a linear function of AH, which it is, according to this equation, but it's actually some more complicated nonlinear function of our features x. So that's really the difference between linear logistic regression and now this enhanced version where we have all this other stuff going on. So we can just come up with a name for the function that takes us from that x to that z. We'll just call it capital F. So it's some function. It's kind of complicated. There's linear stuff, nonlinear, linear again. But whatever, we can just call it capital F. And so this is now our probabilistic model for our overall system. Probability that the label is 1 given x is this sigmoid function where z, or zo, is that kind of complicated function of the original input to this neural network. And that gives us everything we need to do our maximum likelihood training. So essentially, we know that in maximum likelihood, we just want to, or minimizing the negative log likelihood, we can do that as follows. We just need to plug in the specifics of this. And we know that because this negative log likelihood is based on this logistic kind of model, we did the derivation back in Unit 5 that says that takes this form. And again, this ZOI would be from this equation where you'd have XI. Okay, so this is all stuff we've seen before. The only thing that's changing now is the output z is no longer a linear function of x, it's this more complicated function because of all this other processing that we've done. So is that part clear? So one important thing that has changed is previously, when we worked with this model, and z was a linear function, for example, it was this equation here. In that case, this optimization problem was a convex optimization problem, which is great because we know that there's all these ways to solve it. We don't really have to worry about whether we're going to solve it or not. It's just, it can be done. It's not a big deal. Now, the trouble is because of the nonlinearities here, this new log likelihood function is no longer convex in these parameters because of these nonlinearities. And so it's no longer convex in theta, and it's going to be a lot more difficult to optimize. In fact, it's hard to even know if we have ever optimized it because this thing could have so many local minima. This is a pretty big, there's a lot of parameters to design here. We can't really even visualize the space. There could be a lot of local minima. We'll find one. We don't know if that's the best one. There's too many, the space is too big to navigate completely. So these are the kind of issues that are now, we'll have to face when we talk about neural networks that we haven't seen before. So we'll have to talk more about this later. But at least the maximum likelihood procedure, that's the same. That's the same as what we've been doing. In this case, some of the equations are the same. It's just that this part is new, and there are going to be details in terms of how we do the optimization that we'll have to get into. Okay, so, all right, any questions on this? All right. Okay, so why is this called a neural network? Well, when you look at biological neurons, and at least when you look at just a simple model of them, they are these things that they have essentially an output. Okay, so they have these things called dendrites that take inputs. They input currents or charges from other neurons, and then there's this thing in the center, the soma, that accumulates that charge. And once that charge exceeds a threshold, it sends out a charge along this axon. And then that goes to other ones and so on. And you have these currents that sort of propagate through a collection of these neurons in a biological creature. Okay, so if you think about what's happening, it's actually not so different from our model. So the soma, the key idea is that this soma collects charges and only outputs after the charge reaches a threshold. So pictorially, you have something like this, where these are the signals coming in, the charges coming in. Maybe this thing weights them by different amounts. These are some weights that we apply to those inputs, x. We sum them together. We have called this z. And then, if you have some sort of shape like this, that sort of suggests, well, as the charge gets up to a certain point, nothing happens, but then once it exceeds that point, you get a big change in the output. So that's what happens when charge reaches a threshold. So you have this kind of thresholding function. But that's exactly what our sigmoid is, right? It's just a soft version of that. So in some sense, when you look at the hidden layers, they're doing just what these neurons do. They collect charge, weight it. This bias you can think of as selecting where the threshold is placed, and then this is that nonlinear threshold that determines what is put out. So there's a lot of similarities between our artificial neural network and the biological ones, and that's why they've been given that name. Okay, right. Questions? Okay, so just quickly a little history. So some of these simple biological models that we're talking about here date back to the 1940s. And in the 1950s is when people started thinking about artificial neural networks. And back then, the term perceptron was coined, and a perceptron is kind of like a single layer network, very similar to logistic regression, kind of like something like this. But as we know, linear classification, which is what you have with a single layer, is limited in what it can do. And in the 50s, of course, compute was quite limited too. But in the 60s, things got more sophisticated, and people were thinking about more sophisticated things. So this procedure called backpropagation, which we'll talk about next week, was developed. It's an efficient way to train these multi-layer networks. So after, there was a bunch of attention. They call this the first wave of AI. And then things sort of died down. So then 70s and 80s, not really as much going on. Then in the 90s, there was a big resurgence of these ideas. In this case, we had a lot greater computational power. Progress was made. But then after a decade or so, things quieted down again. It's sort of like they hit these stumbling blocks. People were not excited about it. In the 2000s, if you were working on this kind of stuff, you were kind of like a loser. It just didn't seem like it was going anywhere. That all changed in 2012. Now we're in the third wave of AI. We'll get into the details of exactly what happened in 2012 in the next unit, but basically it's when so-called deep networks were really starting to make an impact. And deep networks are like these things, but just many, many layers of this, one after the other. And when you have many layers, you have a lot of weights to train, which means you need a lot of data to do that well. You also need a lot of computational power to do all the computations. But those are things that we have now. And so that's sort of what yielded the breakthroughs. It's not like the methodologies in 2012 were really any different than in the 1990s. There was just a couple more tricks, implementation tricks, but it was kind of the power, the computational power and the data, that's what really gave the opportunity. So the first breakthroughs were in speech and image processing, but then they started happening in many, many more fields. And so that's kind of where we are today, where if you're doing engineering or science or business or just about anything, like it's hard to escape networks, neural networks, deep networks, machine learning. It's everywhere now. So as for deep networks, we're going to talk about that in Unit 9. So we're going to focus on these simpler networks for now, just because there's a lot to talk about here. And let's understand this before we get more complex. Okay, so what we'll do next is we'll talk more specifically about some of the options we have when we construct these things, and also some of the conventions. So one thing that I found really strange when I first started learning about this stuff is pictures like this. These pictures are very different from the pictures that I saw as an ECE student in my training. In ECE, we tend to have diagrams, block diagrams like this, where the signals are the lines and the systems are the squares, or you could make it a circle or whatever. So it's like a signal going into a system and out comes a signal. But somehow in some of the computer science literature, they actually reverse that idea. So now these are the signals and these are the systems. So what's being shown here are the X variables, the raw features. What's being shown in the middle are what we call the hidden AH. And then here are the outputs, maybe A, O. And then all the number crunching, all the processing is actually done in those lines. Okay, so just something to be aware of. When you see a picture like this, it's very different from a picture like this, but it's just sort of coming from a different community with a different history. So as long as you're aware of that, you can interpret these pictures as well. So, okay, so as we talked about, there's these two layers, the hidden layer and the output layer. The hidden layer is kind of like up to here, and the output layer is there. In the hidden layer, the kind of processing we do is we take our raw inputs, we do some scaling and shifting of them, and this gives us one of these scalar, I guess it gives us, yeah, let's see. It gives us this variable, so I'm sort of describing what happens along one of these lines here. The key point is that these activation functions are scalar valued and nonlinear. So you do this linear processing of your feature, and then you put it through a scalar nonlinearity, and then that gives you this hidden output. In the output layer, it's similar but slightly different. So here is the same processing applied, but now we're starting with the hidden outputs. So again, linear processing. But what's a little different is that, and it's actually different from what this diagram implies, the output layer nonlinearities are often, they don't work in this decoupled fashion. So in fact, I think I drew it that way back here. Well, oh no. That picture, there's only a single one. So we're not talking about what happens when there's several yet. But my point here is that when you get those output scores and you put them through a nonlinearity, it's usually not like decoupled scalar nonlinearities. There could be just a joint nonlinearity on all of those that gives you a new vector. Okay, so that's one comment. Another one is that in many cases, this output nonlinearity here is actually optional. If you want to build a network with that in there, you can do so. If you want to build a network without that there, you can also do so. You just have to be sure that you recognize what outputs the network is producing and you use them appropriately. We'll talk about that in just a moment. So again, these are called multi-layer perceptrons, and we're talking about 2 layers. You could use more than 2. When you use enough, you call it a deep network, but for now, it's just 2. All right, so okay, so here's the picture I was looking for. So here's more of like an ECE type block diagram for what's happening. Take your raw features, put it through some linear transform to get these hidden scores. Each one is individually put through this nonlinearity. We'll call that nonlinearity, that nonlinear function H. It gives you, it's called the activation function. It gives you the things called the activations. Then in the second stage, the output stage, you again do some more linear processing. But here you can see that we have a joint nonlinear processing of those to get those. And in particular, the way that I created this is that if you think about those 2 things as the 2 x and y axes, then this would be the vertical axis in this picture, and this is the vertical axis in this picture. And this is actually showing the softmax function. That's actually what it looks like. This would be the kind of typical function that's used in this last stage for a classification network. Okay, so that's sort of how we're constructing these. Any questions on anything? Okay, so let's talk about how we choose this first layer nonlinear function. So this hidden layer activation. There's many choices out there, but these are the ones, the 3 that you probably see most often. The first is the sigmoid, which is what we used a few pages ago in that experiment. And it's the same one that we use in logistic regression. As we know, it's a function that goes from 0 to 1. And when the input is 0, it's halfway, it's 0.5. So when you think about this sort of in the big picture, one of the things you might notice is that the output of this is bounded, meaning no matter what the input is, the output is never smaller than 0 and never larger than 1. So that's sort of an interesting thing about this function. This is sometimes used in shallow networks, never in deep networks though. A very closely related function is the hyperbolic tangent. And the hyperbolic tangent is nothing more than twice the sigmoid minus 1. So it has the same shape except that it goes from minus 1 to 1. That's the only difference. Otherwise, it's identical in terms of its shape. So now, the difference then between the hyperbolic tangent and the sigmoid is that this guy is centered, meaning 0 input gives you 0 output, whereas this one is not. 0 input gives you an output of 0.5. And it seems like this shouldn't really make much of a difference. It's just this shift, big deal. But what you'll find is if you build a neural network with the sigmoid and build one with the tanh, you might find that this tanh works a little bit better. And it's kind of based on these reasons that seem insignificant, but at the end of the day, are all these things that really matter with neural networks. So I think what happens is, we often normalize our data. So when we put our data into the network, we want it to be, in many cases, zero mean, maybe unit variance. And when PyTorch or TensorFlow or these frameworks that have been developed to implement this stuff, they come up with very specific ways to initialize the weights, the WMHCs and so on. And these initializations tend to work well when everything is designed consistently. And the initializations really matter because when you're doing non-convex optimization, if you start from a bad place and you do your gradient descent, it will take you to some bad local minimum and you'll get terrible performance. And I think that was the whole point of the lab in Unit 6, right? You did all this stuff, all this linearization to get a good initialization so that finally the optimization of this nonlinear kind of non-convex thing will converge to a good spot. So with these neural networks, this is also the issue. And little things like whether you correctly normalize the input or not can give you big differences in performance, all because of the non-convexity of the optimization problem you're trying to solve. So that's sort of my belief of what happens. The difference between sigmoid and tanh is nothing but a shift, but that shift, that centering or non-centering, can affect the kind of numbers that flow into these stages that are initialized in a particular way, and if that doesn't really work well with the initialization, you get stuck in a bad local minimum, and the performance is just not that great. So those are a couple of the more popular options. Another option that is, in some sense, quite different is this rectified linear unit, or ReLU. So this is a function where for all negative inputs, it outputs 0, and for all positive outputs, it just outputs the same thing. So this is just an identity function. So it's an interesting function. It's not bounded, right? In the sense that, like, as the input gets bigger, the output gets bigger, so that's different from those other ones. It's also not centered in that, the outputs are always positive, never negative. So it has some peculiarities, and there are ways that people have tweaked this to try to get it centered and so on, and generally it works a little bit better. But it has some other properties that we'll get into in the next unit that make it a really good choice for deep networks. And that was actually one of these little tricks that they figured out around 2012 that made deep networks and this whole third wave possible. Is like little things like ReLU. They prevent certain issues in computing gradients that if you didn't figure this out, you're stuck with. So we'll talk more about that in the next unit. But these are common choices. And if you're working with a two-layer network, they all work relatively well, relatively similarly, some small differences between them. They're all options in the project. You can play with these sort of things. Okay. All right. Any questions on these? All right. We'll come back to this again in the next unit. So that was the hidden layer activation. What about the output layer activation? So this is the thing at the very end of the network. So let's talk about the task we're solving. So let's say we're doing binary classification. Okay, so we actually have, okay, so in this case, we know that the final output is just a scalar, right? That's, for binary classification, we have a scalar score and z. So when z is positive, we think it's class 1. When z is negative, we think it's not class 1. And we know that if we want to convert that linear score into a probability or something like a probability, we can put it through the logistic sigmoid function. And so now we take a score and we actually convert it to probability, something between 0 and 1. So that is definitely one option when you create this neural network, like we did in the demo we talked about a few slides ago. We can put this at the very output of the network, and then we just know, okay, we're going to get numbers between 0 and 1. We can interpret them as probabilities. But you don't actually need to do that. You can leave off this stage, and you can just have your network output the score directly. Because for classification, this is enough, right? You're just going to threshold this at 0. That's the same thing as thresholding this at 0.5. So really the score, the linear score, is all you need to do classification. You don't actually need to convert it into a probability. So both of these are good options. And they're both equally well used. You just have to be conscious of which one you're using, and then you use the appropriate machinery to deal with that choice. Okay. Any questions on this? Okay, so then let's talk about multi-class classification. So in this case, we know that the score is not a scalar anymore. It's actually a vector of real numbers. And typically, this is itself enough to do classification. However, we saw that in multinomial logistic regression, we can convert this to a probability mass function, a vector of probabilities, if we put that through this softmax function. And so that is a very popular option in these neural networks. You have the last stage, which takes that vector of scores and produces a vector of probabilities, a PMF. And so that's sort of what I was illustrating here. So this is your real numbers. Now this is a PMF, so this is a vector of numbers that must all be between 0 and 1, and they must sum to 1 to be a valid PMF. Both of them are equally good for classification, because if you're doing classification and you have this score vector only, that's fine. You just say, well, which of these is the largest? That is what I'm going to report as my guess. You could say, well, maybe this gives you a little bit more information. Not only do you know which is largest, but you know if it's 0.8, then you might say, oh, I think this is like 80% confident that it should be that value. You don't want to buy too much into those confidences because they're not really accurate in that way. It's just a model. So here again, we have a couple options if we're doing multi-class classification. Now, what if we're doing regression? So in the most general case in regression, we're not predicting one target. We're predicting, let's say, a vector of k targets. So k can be really any number, 1 or larger. So let's just take the general case. So now our scores are k-dimensional. In this case, you really don't want to do anything more. That's where you want to have the network end. You don't want to do any further shaping of them. For example, you would not, if you're doing just regression, you would not want to put your scores through this or this, because that would prevent them from ever reaching outside the interval from 0 to 1. So like you would never be able to predict any values outside of 0 to 1. That would kill everything. So, so for regression, you don't use any final layer. You just output those final scores. Okay. All right, so let's just do one more page for today. So the very last thing is, how do we train these networks? What loss functions do we use? So here again, we have to think about what task we're performing, and that tells us both what the output activation could be and what the loss function for training should be. So again, start with binary classification. So we know back from Unit 5. One option is to do logistic regression, which poses this sort of logistic sigmoid model. And then this is the likelihood. It's just where we plug in all of our data, all of our x's and y's. Actually, there should be a an I index on that x. There too. Okay. And then we know that, okay, given that likelihood, we derived back in Unit 5 the negative log likelihood, and that gave us this expression. And we called it binary cross entropy, but I never really explained this term cross entropy. So now I'll give you an explanation. So it turns out that this is exactly how you write the loss if you want to write it in terms of those linear scores. But as we said, if you want, you can put those linear scores through a sigmoid at the end of the network, and you can turn them into these probabilities A, these numbers between 0 and 1. If you do that, you can rewrite the loss in terms of those A values. And when you do, you get a new version of the loss, something we haven't seen before, which has a slightly different form. So these two losses, they're mathematically identical. They're just written in different ways. The first one is written in terms of the z's. The second is written in terms of the a's, where the a's are a function of the z's. But this last one has a kind of a, I don't know, a little bit more of an interpretable structure where you have like y log a, or 1 minus a log 1 minus y log 1 minus a. And this is where it relates to something called the cross entropy from information theory, where you are looking at the entropy between the y's and the a's. And that's where you have this kind of form of y log a. So this sort of explains finally where this name comes from. So either way is fine. It just, you have to use the one that corresponds to how you built your network. So if you built your network to output a z, but then you train your network based on this loss that expects an A, it just won't work well. Likewise, if you build your network to output an A, but then you train it according to this loss that is expecting a Z, again, it won't work well. It will do something, but it won't converge to a very good place and you won't have good performance. So you have the option to do either. You just have to make sure that the way you build your network, how you build that last layer, is consistent with the loss that you use when training. Okay, so that's the moral of the story, is like you have flexibility, but you just have to be consistent. Okay, any questions on this story? Okay, it turns out that the other ones are quite similar. So in the multi-class case, what we derived back in Unit 5 with multinomial logistic regression is that we can write things this way, where this uses this softmax. Then we derive this cross-entropy loss, negative log likelihood. But what we see here is that if instead of writing that loss in terms of the z's, we can compute these a's by putting the z's through the softmax, and then we can rewrite the loss in terms of the a's, and it actually has a much nicer form in some sense. It's just a lot cleaner to look at. So again, both are options. If you construct your network with this as the last layer and you output the a's, you want to make sure that you use this loss when training. On the other hand, if you output z's from your network, then you want to use this loss when training. Both should give you exactly the same performance, the same trained parameters. Everything should be identical. It's just that they're mathematically, alternate descriptions of the same thing. Okay, any questions on this? All right, so then the very last one is regression. So there's many options. The one we focused on most was the model where we say that the targets Y are the scores plus additive white Gaussian noise of a particular variance. And we know that when we did the negative log likelihood of this, that's when we got our quadratic model, RSS. And that is the most common way to set up a neural network is, you just output the z's as the last layer and then you train it to minimize this loss. It's often called L2 or squared error, different names, but I think we're familiar with all those names as well. It's not the only option. For example, you could instead tell it to minimize L1, where instead of the squaring, you have an absolute value. So that's also another option. It's pretty popular in image processing to do that instead of the square. But you can sort of choose however you want to do the loss. There's many, many options available to you. Okay, so that covers things. Next, we'll get into more details about how to do the training, but this is sort of the overview of the architecture and the main ideas. So hope you guys have a good weekend. If you have any questions, you can ask me now. Otherwise, I'll see you on Monday.